University in the Department of Physics and Astronomy, and here are a few points from my career. Did PhD in 2003, did a few postdocs here and there, and then came back for a permanent position in Uppsala. Research interests, obviously stellar magnetic fields, what I'm talking about in this school, but also other things like stellar atmospheres in general, pulsations of stars, astroseismology, determining chemical abundances, determining parameters of stars, and so on. I'm also interested in doing a lot of work in developing instrumentation, in particular instruments for the ELT. And that's how we dress in Sweden when not teaching in Spain. All right, so this is a rough outline what I hope to go through during the 6 hours that I have been allocated. So first I will spend about 2 hours on going through the basic physics that is necessary to understand how we measure and model magnetic fields in stars. So talking about things like Stokes parameters, polarized radiative transfer equation, methods of diagnostics of stellar magnetic fields, and also a little bit about instrumentation, what is the best instruments we can use for stellar magnetometry. And then in the subsequent part, I will jump back and forth over entire chart diagram and talk about recent results and outstanding questions in stellar magnetism. Right, so this is the first part, theoretical basis. And of course, we need to start with defining what is exactly our measurable quantities. And you probably, all of you know that polarization of radiation is characterized with Stokes parameters. And nevertheless, I think it's useful to repeat this basic definition. So you all know that polarization is essentially situation when in the electromagnetic wave the oscillations of the point of electric field vector is not a random but somehow organized, and we can have situation when these oscillations occur along a certain line, and this is this plot, and this situation will represent linear polarization. Then there could be a situation when this electric field vector is going along the circle. That would be a situation corresponding to circular polarization, this plot. And in general, it's a combination of all these effects, elliptical polarization shown here. But in practice, the way the Stokes parameters are defined, there are various approaches. One can use so-called Poincare sphere and other things, but in the observational stellar magnetometry, and I think solar magnetometry as well, this so-called operational definition is very popular. So what it says is basically, let's imagine that we have a certain ideal polarizers, okay? Have something that measures the intensity, measures intensity using a perfect linear polarizer, which makes a certain angle alpha relative to reference direction, okay? And this is what I denote with capital I and this small alpha. And then we can also have the perfect right-hand and left-hand circular polarizers. So what the Stokes parameters are is essentially the differences between intensities measured using these perfect polarizers. For Stokes V, it's the difference between left and right-hand intensity, and Stokes Q is the difference between linear polarization measured along the reference direction, so the reference direction is indicated with this arrow, and perpendicular to the reference direction. And then Stokes U is measured as a difference of the intensity at the angle 45 degrees and at the angle 135 degrees. And then the irregular light, the unpolarized light, Stokes I, would be a sum of each of these situations, like sum of left and right circularly polarized light. Now, what is exactly happening with the atom, isolated atom in the magnetic field? So what I present here is I think this is all familiar to you. This is basically Hamiltonian. It tells you what are the different contributions to the total energy of the atom, of the electron in the atom in the presence of magnetic field. So we have kinetic energy, potential energy, energy responsible for spin-orbit coupling, and then this, in square brackets, comes the contribution due to the presence of the magnetic field. And we have here B corresponds to magnetic field vector, L is the orbital angular momentum, and S is the spin angular momentum. Now the important thing about this particular expression for the Hamiltonian is that different magnitude of different terms determine in which regime we are, and that makes a very big influence. That determines how our polarization spectra look like and what kind of theory we need in order to model observations. In particular, if we have a situation when this term, number 4, the term responsible for linear Zeeman effect, is dominating over the 5th term, over the quadratic Zeeman effect, and still this term number 4 is much smaller than the spin-orbit coupling. This is regime which is most familiar to us. This is a regime of linear Zeeman effect. Okay? There could be a situation when the term number 4 is comparable or even larger to spin-orbit coupling. This is also encountered very often in for special lines and in stars with very strong magnetic fields. This is known as Paschen-Back or partial Paschen-Back effect. And then in very strongly magnetized environments like white dwarfs, we could have a situation when term number 5, the quadratic term in the Hamiltonian, dominates. So the regime of quadratic Zeeman effect. But throughout a very significant part, essentially all that I'm going to present, the description within the linear Zeeman effect is applicable. Now, in the absence of the magnetic field, spectral lines would correspond to a transition between two energy levels, say between upper and lower energy level. If magnetic field is present, you know that energy levels are going to split, and the number of sublevels is determined by the J quantum number of that level. So here I illustrate the simplest possible situation. The lower level is sort of insensitive to magnetic field. It has J equals 0, and the upper level has J equals 1. So the possible magnetic quantum numbers M go from minus J to plus J, so in this case from minus 1 through 0 to plus 1. So what this gives us is the possibility for the electron to perform not a single transition with this energy difference, but 3 different types of transitions. Okay, so obviously this will give rise to 3 different contributions to the spectrum, 3 different spectral line components. So the a component which corresponds to the transition between m equals 0 and m equals 0 for the lower level is known as pi component, and for the triplet line that is illustrated here, pi component is has the same central wavelength as the original line without magnetic field. And then we get also blue shifted and red shifted components, which are known as sigma components. Furthermore, there is these components are also polarized, and this scheme is supposed to show you how this polarization looks like. So this is the vector of magnetic field B, and if we look from the top, if our line of sight is aligned with magnetic field vector, we see only sigma components, and these sigma components are polarized in the opposite sense. So one component would be polarized, would have right-hand polarization, and another left-hand polarization. If we look from the side, like this on this vector B, then we are going to have all three components, pi component and sigma components, and the polarization in the pi component will be linear and orthogonal to the linear polarization in sigma components. So this is the basic setup at the level of individual atoms that corresponds to magnetic field observations in stars. This is what we have to deal with. But in reality, of course, we need some mathematical apparatus to predict spectra of magnetic stars, predict Stokes parameters. And what we use is the so-called, what we have to do is to solve polarized radiative transfer equation. It can be written in various ways, and the way that I prefer here is this one. So I here is the Stokes vector. It's a vector consisting of all 4 Stokes parameters, and it's a column vector, so I have the transpose here. Then the Z corresponds to just geometrical coordinate. And then this calligraphic K is absorption matrix. So absorption matrix consists of contributions from the continuum absorption coefficient, and there is a summation of over all spectral lines contributing to a given wavelength. Okay, so we have this line absorption coefficient KL, and then we have some matrix F that I will describe in future slides. And well, they are added together to the continuous absorption. And then we have emission vector J, which looks like this. So it has the contribution of the source function in the continuum and the source function in the lines. And then there are these 2 matrices. I is 4x4 identity matrix, so matrix with 1s on the diagonal and 0s elsewhere. And then J is this kind of vector. K, C, and KL are continuum and line center opacities, and these are source functions for the line and continuum. Now, to simplify my life and to get through all this in a reasonable amount of time, I make these assumptions. I assume that continuum is unpolarized, which is valid for the vast majority of stars, of magnetic stars. I also assume local thermodynamical equilibrium. That means that my continuum and line source functions are equal and are both equal to the Planck function. So they're just functions of wavelength and temperature. And then I treat here scattering in the continuum as pure absorption. So what is this matrix F? This matrix is the one that encodes information about magnetic field strength and orientation. So it looks like this. It has these different components, and eta components are usually called absorption coefficients, and components which I'm calling rho here are called anomalous dispersion coefficients. And you can see that absorption coefficients, the one corresponding to Stokes I, to unpolarized intensities on the diagonal, and the ones corresponding to QUV are in this upper row in this first column. So this part of the matrix is symmetric, whereas the part with the anomalous dispersion coefficients is antisymmetric. So what are these etas and rhos? How they are related to actual spectral lines? Well, to understand that, first let me define the coordinate system that I'm using where I define angles entering these expressions. So I have my vector B, magnetic field vector, and I'm looking at this vector from the direction of the axis Z, from here. Now the theta angle is the one which is the angle between B and my line of sight, and then the second angle that I need is chi, and this angle defines orientation of the projection of B onto the plane perpendicular to the line of sight. So this is how these angles that are entering expressions here. This is how they are defined. So I split the magnetic field into two components, the one which is parallel to the line of sight and perpendicular to the line of sight. Now, just for the completeness, I give these expressions for etas and rho coefficients. So what is entering here are the quantities phi and psi, and these quantities correspond to absorption and anomalous dispersion in individual Zeeman components. But all information about the magnetic field orientation is actually encoded in these trigonometric functions that you see here. So phi and psi will depend only on the magnitude of the field, on the field modulus, whereas field orientation only is encoded here. So what you can tell is, well, for instance, for Stokes V is somehow sensitive only to the cosine theta, so only to the line of sight component of the field. Whereas Stokes Q and U, they are sensitive to both angles. So they are measuring orientation. In particular, they are measuring orientation of the field in this plane, perpendicular to the line of sight. So what are these phi's and psi functions? These are summation over absorption coefficients and anomalous dispersion coefficients centered onto the positions of Zeeman components. So this summation that is present here is summation over Zeeman patterns. Okay? In the simplest situation that I have considered before, we have only triplet, and that means that for each kind of component, we're going to have only one contribution. So triplet has only one pi, one red sigma, and one blue sigma. So in case of triplet, we don't have summation here, just one entry. Now, this function S represents function that gives the relative strength of the pi components and sigma components. And then functions H and L correspond to Voigt profile and so-called Faraday Voigt profiles. So this is how, in practice, we would compute these contributions to the total absorption matrix. So the Faraday Voigt and Voigt profiles are dependent on the small a. Small a is a function, a parameter giving the broadening of a Voigt profile. More precisely, it gives contribution to the Lorentz part of the Voigt profile. And then we have these ratios of wavelength difference. So this is essentially this wavelength differences are wavelength for each of the Zeeman component, and this is divided by delta lambda d, which is the Doppler broadening. So the Doppler broadening due to thermal motion in the plasma, and the A is where thermodynamics is entering in this case. And of course, thermodynamics is also entering in K, C, and KL, our continuous and line center absorption coefficients. Okay, and Zeeman pattern is described. To describe Zeeman patterns of spectral lines, we need two things. We need relative strength, this S, which is actually calculated through what is known as 3J symbols. And I will not explain what it is, but the bottom line is that you can get a simple algebraic expressions giving for specified M, J, and differences of M values for upper and lower levels. You can get these values of S. And then we have relative positions of the components, which are given like this, where G is the so-called lambda factor of the upper and lower level, and M is this magnetic quantum number. And delta lambda B, which I introduce here, is given actually by this. So it's actually constant multiplied by the field multiplied by the central wavelength. And this constant is given assuming that we measure field in Gauss and wavelength in angstroms. Already from this you can figure out that the magnitude of the splitting grows as lambda squared. So the further we go in wavelength, the more precise, more sensitive we are to the magnetic field. And what is also useful to mention is that the sum of the strength of each type of the Zeeman component is equal to 1. So there is this normalization. Sum of the strength of pi components equal to 1, and the same for the sigma red and sigma blue. So in order to determine Zeeman splitting pattern, what we need to know is J values, and we need to know lambda factors. So these things are usually obtained from databases of atomic line parameters. Sometimes when we don't have information on lambda factors, one can use a simple approximation known as LS coupling approximation to get these lambda factors from J, L, and S quantum numbers. This works usually for lines of light elements, like maybe up to iron. But for heavy elements, this formula is usually not applicable, simply because the energy terms in the Hamiltonian are not corresponding to the LS coupling approximation. This is an example of how different Zeeman splitting patterns may look like, the different lines. So our simple triplet is here, but in reality situation may be much more complex. We can have many pi components and many sigma components, and they can be distributed in different ways relative to the line center. So this is all different possibilities that we can have. In addition to considering individual lambda factors of upper and lower levels transitions, it is usually useful, often useful, to define what is known as effective lambda factor, calculated like this. And this is a good, what it actually tells us is what is the center of gravity of sigma components relative to lambda 0, relative to the situation of the absence of magnetic field. So this number gives a rough estimate of magnetic sensitivity of a spectral line. So it, for actual spectral lines, at least in the optical wavelength range, it varies from, say, 0 to about 3. And most lines have 1.2 with little scatter. Now, this illustration is showing you how Voigt and Faraday Voigt functions look like. So these are these phi's and psi's. And I illustrate situation here for the triplet. So only one function for each type of the component. So for pi component, it is unshifted, and for sigma component, it's shifted to the red and to the blue. Now, there could be, of course, complications to this picture, and the complication that we encounter most often is that sometimes the magnetic splitting is comparable to the fine structure splitting. So the terms responsible for the spin orbit coupling and for the linear Zeeman effect are comparable, or even magnetic term is dominating. And then we enter in what is known Paschen-Back or partial Paschen-Back splitting regime. And such situations can occur when we have two very close lines, like this is the case for famous lithium line. It's a closed doublet. Or it can happen when we have additional type of splitting, for instance, due to hyperfine interactions. So these two figures illustrate examples of complication. So for the partial Paschen-Back splitting in lithium, this is how what we get from the detailed calculations when we consider both terms in the Hamiltonian together. So in the beginning, you see when the field is sufficiently weak, we have these two lines of lithium doublet, And the colors correspond here to sigma components are shown with green, and pi components are shown with red, and the thickness of the lines correspond to their intensity. So in the beginning it looks like more or less linear Zeeman splitting, but then you see what happens. Some components disappear, and then some components deviate from linear Zeeman splitting, and at the end we arrive to a simple triplet. Okay, and these bars here indicate the actual magnetic field corresponding to lithium doublet, this black row of bars. So you see that very important deviations from linear Zeeman regime occur already around 1 kilogauss. So for lithium in sunspots, we need to use a more sophisticated treatment of magnetic splitting. However, of course, for other more widely spaced doublets, much stronger field is needed in order to go into this Paschen-Back regime. And for instance, for sodium doublet, which has exactly the same terms as lithium, we need something like 100 kilogauss field to feel the effect of Paschen-Back. And this is another situation, a situation when we have both hyperfine splitting and magnetic splitting, and in that case, very often what happens is we get many more components. And you see here I show a picture with the pi components on top and sigma components of only one type, sigma r, at the bottom. And note that the scale here is logarithmic. So it's not like all components are almost the same importance, but, well, there are something like 800 components here of each type. So we must be aware of such lines. Now, if we try to bring everything together and try to forget for a moment, for one slide, about formulas, what we really need to solve polarized radiative transfer equation is some input telling us about the structure of the environment, thermodynamic structure of the environment with which we're dealing, the stellar atmosphere in this case. So we need distribution with depth of certain quantities like pressure and temperature. So thermodynamic structure of the atmosphere. We can have a complicated situation with depth dependence of things, of abundances or magnetic field or velocities. This also needs to be prescribed, of course. Then we need information about line and continuous opacities. So that we collect from databases. There are databases of each type, databases for continuous opacity coefficients and for line opacity coefficients. And depending on the temperature, of course, we have different kinds of lines and different kinds of opacity sources in the continuum. And then we need, as I mentioned, additional atomic information for computing Zeeman splitting lambda factors. And then we need to prescribe magnetic field. And that is done by saying what is the magnitude of the field and what is the angles with respect to the line of sight, angle chi, and angle in the plane perpendicular to the line of sight, and angle theta measuring the line of sight magnetic component. So having all these things together, we do the solution of polarized radiative transfer equation, and in general case, this solution has to be done numerically because, for instance, stellar atmospheres are specified usually numerically in a certain grid. And this is example of the actual model atmosphere. Typical situation is when we have atmosphere specified on the grid of certain reference continuum optical depth, in this case continuum at 5,000 angstrom, and this is logarithm of the optical depth, so it goes from around +2 to -5, -6, and this is black is temperature, and red shows the density in this atmosphere. So this is just taken from the grid, which is used very widely in stellar research. Here we have about 4 points per decade of change in log tau. And then for this atmosphere, we compute line and continuum absorption coefficients. So this is illustrated here. Line is black, continuum is blue. And then, essentially, what is the solution, numerical solution of polarized radiative transfer equation? Is a numerical algorithm that allows us to solve this set of coupled differential equations. More specifically, we're given a grid in depth, and we need to propagate our Stokes vector I from point I to point I plus 1, knowing the source function, Planck function, and knowing this matrix containing the absorption and anomalous dispersion coefficients. There are various tools, various algorithms suggested in the past, and they have their advantages and disadvantages. I will not really go into these numerical details. It is sufficient to say that what is important for us is, of course, accuracy. We need to achieve the smallest possible error. And the important thing is that we are usually not able to compute stellar atmospheres with infinite grids, with very fine grids. We usually take what is given to us. So achieving smallest error for a given vertical grid, usually it's quite sparse. And of course speed, as I will show later, we often deal with the situations when we need to repeat these calculations of Stokes parameters over and over and over. So it's important that we have the most efficient algorithm available. And just for your reference, here is papers which suggested various algorithms, at least what is used in most often in stellar research, and in particular the most widely used methods are these three. So this method for 3 year, and then various versions of diagonal element lambda operator. All these things, I repeat, they just propagate for a given absorption matrices. They propagate Stokes I from one point to another. There are some studies which compared different numerical schemes, different methods. For instance, I was involved in one such study. So what you see here is the difference, the arrow difference between the sort of perfect calculation on a very fine vertical grid, and calculation on a more sparse grid for different methods. And columns here correspond to Stokes parameters, rows correspond to different density of points in the stellar atmosphere. So this is highest density, this is lowest density. You don't see details here, but the important point here is that one method seems to be working reasonably well in terms of both speed and accuracy. And this picture is perhaps more clear. It shows the non-magnetic case, non-magnetic test of this method. And actually, the performance in the non-magnetic case is exactly the same as in magnetic situation. So it all depends more or less on how fast with depth your absorption coefficients change. And this is the arrow in logarithmic scale. And for the, well, for some methods you see it's already quite low, this arrow, 10 to the minus 3, this number is, when we have very small number of layers in the stellar atmosphere. But when we refine our atmosphere, we can achieve very good accuracy with essentially any method. Now, as a result of this exercise, numerical exercise, we get Stokes parameters. And this is an example of typical Stokes parameters. So I, V, Q, and U. And the profiles are shown here for different colors correspond to different orientations of the magnetic field vector. So the angles are 0, 30, 60, and 90 degrees with respect to the line of sight and the field vector. And I'm not rotating the vector in the plane perpendicular to the line of sight. So all these profiles correspond to reference direction coinciding with the positive Q direction. And the two panels here, the groups of panels here, correspond to the situation of relatively weak field, 1 kilogauss, and quite strong field of 5 kilogauss. So you can see that the splitting is increasing. One interesting thing that you can notice is that although my magnetic field vector is aligned with the positive Q direction, I nevertheless get some contribution in U, small contribution in Stokes U, and this is due to the presence of this anomalous dispersion coefficients, ρ's, in the matrix, in the absorption matrix. If I would put ρ's to 0, I would get 0 in U. It is also known as magneto-optical effects. So there is some rotation of the polarization due to transfer of radiation. One important aspect that I think is especially important in solar physics is that Stokes parameters have certain symmetry properties. In particular, IQ and U are symmetric with respect to central wavelength, and you can clearly see this here in these plots, and V is always antisymmetric. And, the level of agreement of independent research groups who try to do this kind of calculations, when they agree on the atomic data and on the definition of Stokes parameters and definition of magnetic field geometry, then it's possible to come to the agreement at the level of 2 to 5 10 to the minus 4, and the residual differences seems to come from some deep atomic data which is built in the code, so nothing to do with polarized radiative transfer or anything, like things like partition functions and ionization potentials which are built in the code. So the message here is that we can achieve a very good agreement in independent polarized radiative transfer calculations. Now, all this is fine, but actually it's quite a complicated, numerically complicated exercise to compute Stokes parameters in this way. And it's not immediately clear how properties of the magnetic field, this modulus of B and these two angles that I introduced, how this is influencing the emergent Stokes parameters. So there are various ways to simplify the problem, to cheat a little bit, to say that my atmosphere is much simpler than it actually is. And I will show these ways because some of them are actually used to define magnetic observables for stars. So one of the very popular scenarios is to assume that the source function is given with this linear relation, and this is appropriate for so-called Milne-Eddington atmosphere. And furthermore, we also can, in this assumption, in this atmosphere, we assume that all quantities entering this large matrix are depth independent. So no depth dependence of magnetic field, no depth dependence of absorption coefficients, and so on. And under these assumptions, which are kind of quite strong, and you could say not very realistic, we can obtain what is known as Honorachkovsky analytical solution of polarized radiative transfer problem. And this analytical solution is essentially a rather long expression given how I and each of the Stokes parameters depend on beta, this constant that enters here, the mu, the cosine of the angle between line of sight and the normal to the surface of the star, and this etas and rhos, which are constant. Now, what is happening in reality, in real analysis of data, is that all these complications related to stellar atmospheres and detailed radiative transfer are substituted with analytical formulas containing parameters which are fixed from the atomic line data, the Zeeman splitting pattern, and parameters which are not fixed at all, unphysical parameters like these things. The line strength is beta, and constant A and Doppler width, which are still present here through the Voigt and Faraday Voigt profiles. And it's a big mystery how in papers which are actually using this Milne-Eddington approach, how these parameters are fixed. Now there is I think a little bit of misconception in going on in research on magnetic fields in stars, that Ono-Rojkovsky solution is very good and really perfect. And indeed, the number of free parameters that we are given is fairly large. So 4 free parameters, we are able to reproduce essentially all types of individual calculations of 4 Stokes parameters. But the problem is that this perfect reproduction, or nearly perfect reproduction, works only for a given magnetic field strength and line strength. So if we try to apply the same set of parameters for a wide range of B's and lines with different strengths, we come into problems. And these problems are illustrated here. Well, so we have here a line, the same calculations as shown before, but there are, in addition to that, I plotted as dotted lines the Ono-Rojkovsky solutions. And you see that for this situation, you don't really distinguish the results of polarized radiative transfer done numerically and analytical solutions. You don't see dashed lines behind solid lines, but here at 5 kilogauss you start seeing them. I can remove this difference by tweaking these parameters, but then I get problems on this side. So this is something to remember. I think the books very often say that Ono-Rojkovsky solution provides perfect reproduction of polarized radiative transfer, but what they mean is actually reproduction for only one value of line strength and one value of B. Now, let's go even further. Let's simplify things more significantly. And one very common simplification that is introduced is to say that, okay, my magnetic field is so weak that the Zeeman splitting is negligible compared to the intrinsic line width. Or in terms of this delta lambdas that I introduced before, the effective lambda factor times the magnetic splitting, then delta lambda B, is much smaller than the Doppler width, delta lambda D. In practice, that means that roughly this G times B, the effective lambda factor times magnetic field strength, should be much smaller than this 2.5 kilogauss. Where exactly the boundaries, what is exactly much smaller, it's nobody knows. So some people would apply this even to kilogauss fields, and some would be more concerned. But okay, in this situation, when this is valid, it's actually possible to simplify a lot the polarized radiative transfer equations and come to the conclusion, which I will not show here, this derivation, but one can figure out that to the first order there is no effect on Stokes psi at all. So Stokes psi remains as if magnetic field is not present at all. And the signal in Stokes V, the Stokes V parameter, can be computed in this way. So delta lambda B times the effective lambda factor times cosine of the angle between line of sight, and multiplied by the derivative of Stokes psi. And if I plug in the numbers, this is the formula that I can, equivalent formula that I can derive. So this formula is actually in the heart of many methods to derive magnetic fields in stars. Weak field approximation. If in addition to weak field approximation, we also introduce so-called weak line approximation, we assume that the ratio of the line to continuum absorption coefficient is much smaller than 1, then we can approximately say that the Stokes psi is nothing but the 1 minus some profile that describes the absorption. It can be simply Gaussian, like I'm assuming here. And in that case, well, I can analytically, of course, compute the derivatives of the Gaussian here. And in that case, for weak lines, I can also write down a similar expression for Stokes cube. That will look like this. So B perpendicular would be the field perpendicular to the line of sight. And this capital G with a bar is some kind of parameter similar to the effective lambda factor, but the parameter which gives sensitivity of a given line to, characterizes magnitude of linear polarization in a given line. It's also computed from the lambda factors of upper and lower level and from G quantum numbers. For simplest situation of triplet, this large capital G equals G squared, the small G squared, so it's effective lambda factor squared. Well, here again, I would like to emphasize that this proportionality between Stokes V and the derivative of I is valid in the weak field and any line strength, whereas proportionality between Q and the second derivative of the absorption coefficient is valid only in weak field and weak line situation. So this is more restrictive. Now, if I would be a solar physicist, this is where I would stop. Okay, I have all apparatus to interpret observations of Stokes parameters and derive magnetic observables and say what is the field strength and orientation and so on. But in stars, situation is more complex. We should remember that we don't resolve surfaces of stars. We see them as points. And in fact, what we record with our instruments is disk-integrated Stokes spectra. So what is going on is that we should imagine the surface of the star divided into small areas. And in each of these areas, magnitude and orientation of magnetic field can be different. So like B pointing this way in this area and the other way here. And in addition to that, stars usually rotate. So there is an overall Doppler shift related to this rotation. So in this case, if the star rotates counterclockwise if we look at it from the visible pole, then this part of the star, this half, is going away from us. So it has the contribution of radiation from that star is redshifted, and from the other side it's blue shifted. And furthermore, there is also the effect called limb darkening. So the supposed to be illustrated here with sort of darkening of this image. So there is at each given view we have different mu angles corresponding to the center of the disk and to the limb. So effectively what this means is that we are seeing spectra originating from different heights in the atmosphere. Higher towards the limb and deeper close to the line center. So for these two small areas, we can get very different Stokes parameters. So here, for instance, I assume that the vector of magnetic field is mostly oriented along the line of sight, so I get large V, smaller linear polarization, and I get a redshift, so this dashed line corresponds to unshifted position of the line. For the other surface element, I can get quite different situation, blue shift, and for instance, higher polarization in Q and U. And all these things summed up over the stellar surface can give very non-trivial results. So first of all these things about universal symmetry characteristics of Stokes parameters, all this is gone. Unless we have zero rotation, unless the star is not rotating, then we can't say anything about symmetry properties. For instance, this is illustrated here. If I have a very simple situation, two spots with radial field, and then I integrate over the surface, I get some Stokes I and Stokes V signal, but if I get the radial field spots with a different orientation, like shown here, the resulting Stokes V parameter after summing up of a visible surface looks completely different. That's how it will look like. And furthermore, this signature is very sensitive, this symmetric signature is very sensitive to the rotation of the star, to this additional Doppler effect due to rotation. So if I make the star rotate a bit faster, actually what happens, of course, the Stokes I, as you understand, will get broader due to rotational broadening. But look what happens with Stokes V. Stokes V increases in amplitude because these contributions are more separated in wavelength. And if I rotate the star even faster, the profile shape changes further. So I think here I would stop. The bottom line is that things are more complicated for stars because we need to do this integration over the surface. Okay. Yeah?